Hello. Okay, geez. I was talking and my thing was muted. Hey, everybody. This video is going to cover section 3.6, excuse me, which deals with combining functions. And there are two different ways that we are going to be combining functions. The first one is arithmetically, which is where we are going to be combining the functions using the regular operations, addition, subtraction, multiplication, and division. And when we are adding, this should be a parenthesis, not a zero right here. It's g of x, like that. When we are adding functions, we'll be combining like terms. Subtracting functions is going to involve changing the signs in the second function and then combining like terms. When you are multiplying, you're going to be doing distribution and then combining like terms. And then when you do division, you're going to just see if it can be simplified at all. If not, you'll just write one function on top of the other one, and then that'll be that. There are also two different ways that we are going to do arithmetic combinations. One of them is with a given value, and the other one is without a given value. If you have a given value, typically you're going to get a value as your output. And if you have no given value, typically you're going to get an expression. So I want to do with a value first. So I'm going to scroll down a little bit here because the second ones here are given a value, and then we'll go back and do without a value. Now, when you are combining these different functions in algebra of functions, which is what this is, the operations with functions, you're going to evaluate each function individually at the input value. And then once you have the outputs for both, you will do the combining with the operation. So, for example, in this first one, we want f times g of 2. And what that means is f of 2 times g of 2. So we need to figure out what f of 2 and g of 2 are, and then use their outputs to multiply and get your final answer. So I'm going to start with f of 2. And f of 2 plugs 2 into the f function. So 2 squared minus 3 is 4 minus 3, which is 1. And then we do g of 2 as well. And we get 2 times input 2 plus 1. 2 times 2 is 4, plus 1 is 5. Now, as soon as we have our two outputs, here's my one output, here's my second one, now we're going to complete the operation. So I take f of 2, which is 1, and multiply it with g of 2, which is 5. And 1 times 5 is 5, and this is your final answer. So f times g of 2 is 5. So our final answer here is a value. Whoa, that's kind of crooked, but I guess it doesn't matter. In this second one, we are doing f divided by g of negative 1/2. So again, what we're going to be doing here is taking f of negative 1/2 and then dividing it by g of negative 1/2. And so f of negative 1/2 first. So f of negative 1/2 is, plugging in negative 1/2, negative 1/2 squared minus 3. Negative 1/2 squared becomes positive 1 over 4 minus 3. And at this point, if Hawks is okay with it, you can change it into a decimal, or if they want a fraction, you can leave it as a fraction. I'm going to leave it as a fraction since that's the more involved of the two. And that means I need a common denominator because I'm taking 1 over 4 minus 3 over 1. Common denominator here is going to be 4, so I'm going to multiply a 4 over here. And I'm looking at 1/4 minus 12 fourths, which is negative 11 fourths. So there's my output for the first part. Now I need to do the same thing with g, plugging in negative 1/2 in the g function, g of negative 1/2. So negative 1/2 going in here, 2 times negative 1/2 plus 1. 2 times negative 1/2 is negative 1, plus 1 is 0. So now I'm supposed to take the F output and divide it by the G output. You can probably see that there's going to be an issue here. F divided by G, that's a Q, Jesus. F divided by G, there we go, is negative 11 fourths divided by 0. And you cannot have a 0 denominator. So because there is a 0 denominator here, this is undefined. It does not exist. So we're not going to get an output for that one. And that happens if you're going to have a 0 denominator. So just kind of be aware that it is possible to have a situation where you get something that's not defined. All right, so now that we've seen with a value, I want to scroll back up and do without a value. This is where we are actually working with the functions themselves. And we're going to start with f minus g of x. That means we're going to take the f function, so x squared plus 3x minus 8, and subtract out the g function, 4x plus 5. When you see this notation where it has the two functions and then an x in the parentheses, all that means is you're not going to have a value to go in. So instead of putting anything in, you use the function itself. You are not inputting an extra x or anything like that. There's already an x in here. It's just the notation that means work with the functions, not a value. So I've got the f function minus the g function. And now with subtraction of polynomials, we have to make sure that we change the signs in the second polynomial. We are adding the opposite and then combining like terms. So for our like terms here, we have an x squared. There are no other x squared, so that one's going to stay. We have a 3x and a minus 4x, which is negative x. And then we have a negative 8 and now a negative 5 because we distributed that negative in here, and that's negative 13. We do not do anything with this final answer once we combine the like terms. If the like terms are combined, you're done. So there's subtracting. If it was adding, we would have done something similar, except we wouldn't have the signs in the second one. We would have just combined. This one is multiplication. Again, no value, which just means work with the functions themselves. Multiply these functions together. So x squared plus 3x minus 8 times 4x plus 5. And we're going to have to do some distribution. I'm going to start with the x squared and take it through this second polynomial. X squared times 4x is 4x cubed. X squared times 5 is 5x squared. Pick up the second term and go again. 3x times 4x is 12x squared. 3x times 5 is 15x. Last term, negative 8 times 4x is negative 32x. Negative 8 times 5 is negative 40. Now, once we do all the multiplication, we've got this big long line of terms here. We want to go through and combine any like terms and get this thing in simplest form. So let's see. We start off with the 4x cubed. There are no other x cubes here. Then we've got a 5x squared and a 12x squared. When we combine those, we get 17x squareds. Then I see a 15x and a minus 32x. So 15 minus 32 is going to give me negative 17x. And then the last term there is a constant. There are no other constants in here, so we've got a minus 40 that we kind of tack on there at the end. And again, this is going to be your final answer. You don't do anything with it. You're not factoring or anything like that. We're just combining the like terms and then leaving them as they are. So these are the operations with functions, with a value and without. If we scroll down, we're going to talk about finding the domain of functions and their operations. Now, domain of functions themselves is something that we've already discussed. What we are going to do at this point, though, is find the domain of the combinations of these functions. Now, if they ask you to find what the operation is and the domain, then you can look at what you got whenever you do the combination first. If they only ask you for the domain, you don't have to do the combination. There's a way to find the domain without actually even knowing what it looks like when you put these things together. So here are the steps. And the first thing that we do is find the domain of each function individually. And those rules were rules that we already followed back when we initially talked about functions and domain of functions. In this class, when we are dealing with functions and domain of functions, the only two types of functions that we worry about are square root functions and rational functions. If your functions are anything other than those two things, then your domain is going to be all real numbers. So, for example, in this particular example, we have a linear function and a square root. Now, square root functions are one of the ones we have to worry about, but linear ones are not. So, the domain of f of x is all real numbers. Negative infinity to infinity. For the square root function, we have to actually find it. Now, if we think about the square root function, this is g of x. Square root functions are not allowed to have negatives under the radical, because then we get into the imaginary world and we're dealing with complex numbers. This is in the real world with real number answers. So for g of x, we have to be concerned with where the radicand is negative. To solve the problem of possibly running into a negative radicand, you're going to take whatever is under the radical and force it to be greater than or equal to 0. If this is an expression, you'll have to solve it. In this case, it's just an x, so we already have it solved. X has to be greater than or equal to 0, which means the domain is square bracket 0 to infinity, everything bigger. So there's the domain of each one of my pieces individually. Now, step 2, graph each domain on a number line by shading it on the number line. So I'm going to make myself a number line here. I can get my little thing here. Here's my number line. And on my number line, I can just put some whatever I want on it. I want to make sure that it has 0 on it so that we can shade the second one. But let's say here's 0, 1, 2, 3, 4, 5, -1, -2, -3. The domain of f of x, I'll do in blue, is all real numbers. Well, that's easy. All real numbers is the entire number line from one side to the other. So there's the first one. Then we can look at the domain of g of x. I'll do that one in green. The domain of g of x is square bracket on 0, shading off to the right. Everything greater. Once they are both on the number line, we are going to look at where the shading overlaps with each other. This overlapping part is the domain of these two functions added together. So this thing overlaps right here from 0 on off to the positive direction. None of this counts because this stuff is where it takes our second function into negatives, which aren't allowed. So the domain of f plus g is square bracket 0 to infinity. Important side note, if one of your two functions has all real numbers and the other one has an issue, then the domain is going to be whatever the other one was. All real numbers takes up the entire number line. There's no restriction. So if you have to restrict it for the second function, that's the one you're going to base your domain off of. But this is how you can do it to take a look at it without actually having to find the sum or difference or whatever the case is. Another important side note, when we are dealing with these functions, as long as they are functions, which they are, f plus g, f minus g, and f times g will all have the same domain. So we found the domain of f plus g. This is also the domain, that's a B, the domain of f minus g and f times g. So all three of these things would have the same domain. If you find one, you've got all three. With division, there's a little bit of extra that we have to worry about. Because again, in division, we can run into the situation where our denominator is 0, and that's not allowed to happen. So you want to start with the overlap that we just found, always. For divided by, start with the overlap. But now we have to remove what makes the function undefined. And what makes the function undefined is where the denominator equals 0. So we have to be concerned with where the bottom one equals 0, because that also has to be removed. Does it have us actually do this? Oh no, it has us do it in the second one. Okay. So here we go. In this example, not only does it have us find the formula for each one, it's going to have us find the domain of each one as well. And we want to do f plus g of x and f divided by g of x. So right off the bat, I'm going to list the domains for each one because I can. F of x is a quadratic. Quadratics have no issue, so we don't really have to worry about that one. G of x is a rational, and that one is one of the ones that we've had to deal with. So because the first function, f of x rather, domain, f of x is a quadratic, so domain is negative infinity to infinity. The G domain is the issue, because in the G function, we have a rational expression. So in this rational expression, we want to find out what value makes a zero denominator and remove it. To do this, you are going to take the denominator and set it equal to 0, and then solve. To solve this easy basic equation, we're going to add the 5 over. So x is 5 is the value that is no good. In interval notation, that looks like negative infinity up to 5. Cut it off there. Union. Start on the other side of 5 and keep going off to positive infinity. The 5 round U5 is cutting out that value. You're not allowed to touch it. So there's the domains of each one individually. All right, let's find our formulas here. We're going to start with f plus g, because that's the first thing we're supposed to find. So first things first, f plus g of x. I take the f function, 2x squared over 1. Add in the g function, 2 over x minus 5. And now this is a rational expression. And in rational expressions, we have to have a common denominator. So the common denominator between these two pieces is x minus 5. That means I need one on the top and on the bottom. And I distribute here on top. 2x squared times x is 2x cubed. 2x squared times negative 5 is negative 10x squared. And then plus 2 from the other side all over x minus 5. This expression here is the formula for the sum of these two functions. So there's part 1 done, the formula. Second part gets into finding the domain. So I'm going to draw myself a number line again. Here's my number line. So I'm going to put some stuff on here. So let's see here. We've got, let's do 3, 4, 5, 6, 7, 8, 9. We already said that the F domain is all real numbers. So the whole number line shaded. The G domain is the one that actually has the issue. It's negative infinity to 5 and 5 to infinity. That means we are cutting out the 5 and going off in either direction on either side. I wish these like highlighted better so you could tell the overlap. But it's overlapping where you see the green and the blue. So again, if one of them's all real numbers and the other one has the issue, the domain is going to be the other one. The overlapping part of this is only what is set up in this restriction. So domain for this part is negative infinity to 5, u, 5 to infinity. And there's the second part. So we found the formula and the domain for f plus g of x. Now we've got to find the formula and the domain for f divided by g of x. So, second part. f divided by g of x. That means I'm going to take the f function, which is 2x squared, and divide it by the g function, which is 2 over x minus 5. And now we have to do a keep it, change it, flip it scenario here because we've got a complex fraction. So we keep the 2x squared over 1 times, flip this guy over, x minus 5 over 2. This has now become a multiplication problem, and the 2's are going to cross cancel each other out, leaving me with x squared times x minus 5. And I can distribute this and get something nice. X squared times x is x cubed. X squared times negative 5 is negative 5x squared. So there's your division. And now the domain, oops. Oh, there we go. Now the domain of these two functions, if we're going based on what these rules said up here, we start with the overlap from the original, and then we're going to take out what makes this function undefined. In this scenario, the denominator of the original function here, g, we would have to see where this function would equal 0. So what I want to do is show this out because you're going to see something happen here. We already know what the overlap looks like. We just need to take a look at what this does when we set it equal to 0. 2 over x minus 5 equals 0. Now, to solve this thing, we would have to multiply the x minus 5 over to the other side. But when we do that, times x minus 5, that's going to cancel, times x minus 5, we've got 0 times an expression, which cancels, and it leaves you with 2 equals 0. This is not true. And if this is not true, then there is no value that is going to make that expression equal to 0. So we don't have to add anything extra in to this scenario because there is no value that also causes an issue with the denominator. So if there's no additional information to be brought into this scenario, then the domain is just going to stay the same. So negative infinity up to 5, union 5 to infinity. If there was a value that made that entire function turn into a 0, we'd have to add that in as well. But since there's not, we're in good shape. There is a second example here for addition. It looks like then we get into examples for subtraction. Let's look at this other addition one. Okay. We have to do the same thing that we did before. F plus G, domain, F divided by G, domain. So starting off with F plus G. We are going to take the F function, which is x cubed plus 4, and we are going to add in the G function, which is radical x minus 1. Now, I know it looks weird, but there are no like terms in this thing. So all of this in this odd looking format is your sum of these two functions. If there were like terms, we would combine them, but since there aren't, that's really it. There's nothing we can do here. So that's that. For the domain, we want to begin with the domain of each one individually. So the f of x function is a cubic, and a cubic is not one of the ones that has an issue, which means that the domain of f is negative infinity to infinity. The second one is a square root function, and the square root function is one of the ones that we had that had an issue. So to figure out what the issue is, we have to take the radicand, x minus 1, and force it to be greater than or equal to 0. Then we're going to solve this basic linear inequality by adding 1 over, and we get x has to be greater than or equal to 1, which means that the domain is square bracket 1 to infinity. So there's the two individuals. Now, if I want to put them together on the number line to take a look, I'm going to create myself a number line, maybe, yes. And I will put some stuff on here so that we can take a look at this graph. So let's say we have negative 3, negative 2, negative 1, 0, 1, 2, 3. All right. So first one is all real numbers. Domain of f is all real numbers. Domain of g is 1 to infinity square bracket. So square bracket 1 to infinity. The overlap is happening over here where the green and the blue can both be seen. So the domain of the sum is square bracket 1 to infinity. And that'll kind of be our jumping off point whenever we do the division. So there's the first part done. Let's take a look at the second part involving the division and what happens there. So second part is f divided by g. Now in this scenario, we're also going to end up with something that's weird looking. We're going to take x cubed plus 4 and put it on top. We're going to take the radical and put it on the bottom. And then we can't do anything with this either. We've got a cubic on the top and a radical on the bottom. And that's that. So there you go. This is the division. In the division ones, we build off of the original domain that we found. So in this scenario, not only do we have to be concerned with this stuff here, we also have to be concerned with where the denominator of this function is equal to 0, because that's going to create an undefined situation. So I'm going to take the entire denominator, not just the radicand, the whole thing, and set it equal to 0 to find out what the excluded value is. So radical x minus 1 equals 0. First thing we have to do is remove the radical. So we're going to square both sides. That gives me x minus 1 equals still 0. And then to get x by itself, we're going to add the 1 over. So I get x equals 1. This value is the excluded value. So that means that in addition to this stuff here, which basically just removed this entire side of the graph, I now am also not allowed to touch 1. This thing currently has a square bracket, which means I am touching 1. To solve that problem, round it off instead of square. If I make this thing round, that means I'm not touching it. I'm just getting real close to it. And then everything else is good on the right. So the domain of the division is round parenthesis 1 to infinity. In the subtraction problem, you're doing similar exercises. This time we have a quadratic and a cubic. Both of these domains are negative infinity to infinity. So the only restriction would come from when you divide by the f function. And this time it's g divided by f. So it's a little tiny bit different. I'm going to have to pause here and come back at a later time because I have my tutoring sessions now. So the rest of this stuff, including this one and all this composition stuff, is going to be in a second video for this section. So be on the lookout for that. But for now, at least that'll get you started. And I'll see you guys soon.